So we've just gone over Dalton's atomic theory, and the first part of it said each atom is composed of tiny indestructible particles called atoms. Well, that's not quite true because we know about electrons. So this was the first correction, maybe is the right word, to the atomic theory. But so who discovered the existence of electrons? This guy's name was J.J. Thomson. No P. Thomson. And he used a device called a cathode ray tube. And I've got another video that kind of shows you what a cathode ray tube is. You should watch it. I'll show it in class. And so in the cathode ray, the tube is a vacuum, and they're going to run some electricity through this vacuum, and then the screen is going to glow when electrons hit it, and you think that it's a beam of light, but then if it's light, they put a magnet on there, and the magnet bends it, so it's definitely not a light. So we said that atoms, they were supposed to be indestructible. But obviously something that's smaller than an atom, which we call an electron, is present. So they're not indestructible, they're composed of smaller particles. So he says that these particles that are in this cathode ray that bends to a magnet have some properties. They travel in straight lines because it looks like a beam of light, and they are independent of the composition of the material where they form, which would be the cathode. So it doesn't matter what you make the cathode out of, whether it's gold or silver or copper or zinc or whatever, you're still going to get this beam of light looking thing. It's not actually light. And then he said they carry a negative electrical charge because it's easy to see when you have a magnet which is the positive and which is the negative end. So the positive end bent the light towards the magnet, the negative end repelled it. So he said, oh, it has to be negative because that repels it. So he determined a charge to mass ratio from there. Now, he got a Nobel Prize for that. Now let's talk about this other guy named Robert Millikan. And Robert Millikan, this is called the oil drop experiment. And so this is actually his setup. And what he did is he sprayed these really fine droplets of oil, and he uses positively charged plate to control how far they fall. And then he had a negatively charged plate down here, and so obviously positive and negative are going to control how fast these things fall. And what he did was he blasted them with some radiation, and so they had some charge. And so he determined how big each drop was and how much charge it had. So what ends up happening is he's looking at it, and they're doing these measurements. So he ends up with this graph. So here's the mass, and here is, let me scoot this up a little bit where you can see it better. Here's the charge. And so if it had a low mass, it had a low charge. And so he ends up getting something that looks like the stair-step graph. Well, so you get this stair-step graph, which is what a greatest integer function. And so what he found out was each one of these steps was the same length. same height. So he said all of these drops have a whole number of electrons. So say this was 1 electron, it's not, but let's say 1 electron, 2 electrons, 3 electrons, 4, 5, 6, 7, whatever, because of this radiation. So he said, well, the distance between each one of these stair steps is 1.60 times 10 to the negative 19th, and we use a capital C. This is not degrees Celsius. Capital C stands for coulombs, which that is a unit for charge. We'll come back and talk about that in unit 4 and 180 in chapter 19. So what did he measure? He measured the actual charge of 1 electron. So the charge of 1 electron is 1.60 times 10 to the negative 19th coulombs. Now you can write this on your conversion sheet. I will not ask you test questions about it, but there might be homework problems about it. So that would be a nice conversion factor. So you would say 1 electron equals 1.60 times 10 to the negative 19th coulombs. Make it a fraction, however you need it for your units to cancel.